Thank you very much for inviting me. So I guess I'm the odd one out in this session. I am not working on topics in cosmology. I'm working on topics around machine learning and uncertainty quantification, machine learning and confidence intervals. So I'll be presenting sort of an overview of a recent line of work on how to sort of like merge together machine learning algorithms with the ability to construct valid confidence intervals, hoping that some of these techniques could find applications to problems that the other speakers have described. Okay. So to give you the broad framework of where around the bias machine learning, let me give you a very abstract problem, and then I'll jump into some motivating examples from, mostly from the work that we've been interested in around causal inference. So what's the semi-parametric inference framework? In semi-parametric inference, you have data that, let's say we assume that we have IID data, some random vectors, Zi. And what we care about is some parameter of interest, theta 0, could be some of those cosmological constants that we care about. But in order to estimate those parameters theta 0, we also need to learn some other unknown non-parametric function, G0, of our data generating process, which could be either some generative model or some other non-parametric aspects of the generative model. And if we could estimate that parameter G0, then that nuisance function G0, then we could write down our target parameter as some summary statistic of that non-parametric component. We will call it like some functional of that non-parametric component G0. And what we want to be able to do is first to be able to use machine learning or high-dimensional statistical techniques to learn that non-parametric component G0 from the data, while being able to either prove that we can get parametric rates for the target parameter of interest, even when we don't have parametric rates for that non-parametric component, and being able to construct confidence intervals for that parameter of interest because we want to do hypothesis testing, we want to construct, we want to do science and construct confidence intervals for that target parameter. My main interest on why studying this problem typically arises from causal inference. So even though this is not a cosmological data science problem, let me give you an overview of a basic problem in causal inference that takes is a special case of that general framework. So typically in causal inference, we care about understanding what is the effect of some variable and some outcome of interest. So one way to think of both causal inference is that nature generates two potential outcomes, so y1 and y0. y1 is the outcome that we would have observed from a unit had we treated them, and y0 is the outcome that we would have observed from the unit had we not treated them. And what we observe in the data is the outcome for the treatment that was assigned to a particular unit and the treatment assignment. And what we care about is understanding that difference between the two potential outcomes in average over the population. So that's the target parameter of interest or the average treatment effect. One way to identify that average treatment effect from the data that you have is to make this many times strong assumption, but many times used assumption, that you also have auxiliary variables x, typically known as controls, that are the only variables that affect the treatment assignment. And once you condition on x, your treatment assignment is as if it was from a randomized trial. So that can be written as saying that these potential outcomes are independent of the treatment assignment once you condition on x. If you're willing to make that assumption, then you can write down your average treatment effect as a functional of a regression function that you can train on the data. So what is that functional? You're going to train a big regression function that tries to predict the outcome from the treatment and the controls, and then you're going to average the difference in predictions of that regression model when you flip the treatment variable on and off and on average over all of the other covariates. Okay? So in order to estimate the target parameter of interest theta 0, I now need to learn this non-parametric regression function. Many times those covariates x will be high dimensional, and so you end up with a high dimensional non-parametric regression problem, even though you care about this single parameter, scalar parameter of interest. And so this is how you would write this, this functional for this average treatment effect. You care about the average difference of that prediction model on average over the covariates x, where this prediction model is the conditional expectation of the outcome given the treatment and the covariates. And you want, because of that, because X could be high dimensional, or you want to be flexible and avoid model misspecification when you're doing inference, you want to use ML techniques to learn that regression function. Another place where this arises, even if you don't care about causal inference, the exact same problem arises in sort of explainable machine learning, where you just try to predict an outcome Y, and you're trying to understand how does a particular variable among your variables affects that prediction. Right? So this is typically called the partial dependence. So you have some arbitrary predictive model, and you want to understand how does a single variable affect the prediction on average in the population limit. Or if that variable is continuous, you might care about how does the average derivative of the function, like with respect to that single variable, what is that average derivative, which would give you some sort of like influence of that variable on the outcome of interest. So what do you want from your estimation procedure? You want from your estimation procedure to allow you to construct confidence intervals for that target parameter of interest. So you want to construct some estimator for the parameter theta hat, where, like ideally, if you want to have a simple method for confidence interval construction, would have a nice distributional limit. So if you scale the parameter of interest appropriately with the root of the sample size, and you center it around its true value, then that should converge to some Gaussian limit, so that then you can build standard confidence intervals by looking at the standard error and doing plus minus 2 times the standard error. Oops, sorry. Okay. So what's the natural estimation algorithm? Well, the natural estimation algorithm, let's just train our machine learning model on the data. Let's get an estimate G hat from the data. For instance, let's run a random forest that predicts the outcome from the treatment and the covariates. And then let's just take the average of the random forest predictions over the covariates X. Suppose we do that in very simple examples. You can create very simple examples of data generating processes where the treatment has 0 effect. But if you repeat this experiment many times, the distribution of the treatment effects that you're going to get looks like this. Which means that consistently, your estimation method will give you a non-zero positive treatment effect with statistical significance. Okay. And so this is problematic from the perspective of science. You can't just take a random forest, plug it into in a plug-in manner, and then hope that your target parameter of interest will have nice distributional limits and that you can construct confidence intervals as you would typically do, ignoring the fact that you run an ML algorithm to estimate that non-parametric component. Well, you might say the problem with this natural algorithm is that I reuse the data. I feed in my random forest on the same data on which I averaged, and so maybe there's some overfitting. So one way to solve this, okay, maybe you split the data in half, you feed your random forest on half of the data, you calculate your target parameter on the other half, or if you're a bit more clever, you do a k-fold cross-validation, where you train your model on one fold, you predict on the other, you train on the other, you predict on this one, and then take an average over all the data. Okay? So even if you do that, you still get the same problem. So it's not data reuse that was the problem. The problem is that random forest algorithms with, say, some like cross-validation or model selection, they typically trade off bias and variance, and they trade off bias and variance in roughly the same manner. And so the amount of bias that you should expect your random forest predictions to have is similar to the amount of variance. And this bias variance, this equal bias and variance, will propagate to your target estimate because there's nothing that corrects for biases in G hat in your formula for theta hat. And so your theta hat estimate will have the same amount of bias as variance, typically. And so your confidence intervals, yes, your parameter will converge to the true thing, but it will converge to the true thing in a manner that the sort of the variation of the estimate will be of the same order of magnitude as the bias of the estimate under repeated samples, and hence naive confidence intervals won't cover the true parameter of interest. Okay, so when can you claim that your estimate is asymptotically normal and you can construct nice confidence intervals? Well, the idea in the bias machine learning is that you need to slightly change the formula for your target parameter of interest to correct for biases in your non-parametric estimate. And that's the AD&D bias machine learning. So let me give you, like the basic principle in this average causal effect example. So the problem in the average causal effect example is that the formula we have for the target parameter of interest is very sensitive to variations in that non-parametric component, meaning that any bias or error in our estimate of G directly propagates as an error in the estimate of the target parameter. The idea is that we can add a correction term to our formula that doesn't change what we're identifying, but whenever our estimate of G is erroneous or has consistent bias, it removes that bias from our target parameter. How should we do that? The idea is that we know what our regression function should satisfy. Our regression function is trying to predict the target outcome y, and so we know that if we take the residual of that regression problem, conditional on the covariates, the residual of that regression should be mean 0. And so we can add to our formula any weighted function of that residual. This is not going to change the quantity we identify, because when G0 is the correct thing, this correction is going to be 0. But when G moves away from its true value, this is a hint that your regression is mistaken consistently in that region of covariates, and you should correct the target parameter of interest in that regime. How should you correct it? Well, that comes this weighting function over here that tries to take errors in the prediction and translate them into errors in the treatment effect. So how should that weighting function look like such that this is satisfied? Well, that weighting function should be a function such that whenever you give it a regression function G, and you take the weighted average of that regression weighted by this function A0, it gives you back the treatment effect as evaluated with respect to that regression function. That's what it means that A0 takes prediction errors and translates them into treatment effect errors. If you could find such a function, such a weighting function A0, then note that this formula over here is now not sensitive to errors in G. Why? Well, even if G is very wrong, suppose that G was 0, our regression was completely erroneous, then still we get this alpha 0 times y as our target parameter, and we can do a Tower rule, and this now is the true regression function, and so we can replace this with G0, and by this property, this evaluates back to the true average treatment effect. Does that function A0 work? Does it exist? Well, it does exist for this problem. It's what's known as the inverse propensity score. But the nice thing is that such a function A0 always exists for many target parameters of interest. So to give you a broader framework going beyond this average causal effect example, suppose that your target parameter of interest was any linear functional of a regression function. Linear functional meaning takes, like it satisfies linearity with respect to G. Then the corrected formula for that linear functional is of the same form as I described, with some weighting function A0. The average causal effect was one example of such a linear functional. And by the Riesz representer theorem, any linear functional has an inner product representation. And so what this inner product representation property of that Riesz representer is exactly the property we wanted from our weighting function A0. Whenever you give it a regression function, you take an inner product of that regression function with A0, it gives you back the moment you care about, or the functional you care about, evaluated at that regression function. And so for any linear functional, you can correct your original formula using this Riesz representer approach. Now, how does that Riesz representer look like? First of all, before I tell you about that, if you could estimate the risk representative in the regression, then you can also prove asymptotic normality statements. So, for instance, suppose that you have some regularity conditions about your functional, and suppose that the product of the errors of your regression estimate and your risk representative estimate converges to 0 faster than 1 over root n. Now here, observe that even if these estimates converge to 0 slower than root n rates, so with non-parametric rates, this requires only the product of these non-parametric functions to go down to 0 as 1 over root n. And so this will hold even when you have slower than root n rates for your regression and your risk representer. Then you can prove that your final estimate based on this corrected formula will be asymptotically normal and your confidence intervals will be accurate. Even if you're not willing to believe this property over here, you'll still get that this estimate depends only on the product of these errors in terms of mean squared error, and so you'll get a faster rate for your target parameter than the naive estimate you would have done with a plug-in approach. So even if you care about confidence intervals, you need to make such an assumption. If you only care about estimation errors, this debiasing approach still gives you some faster convergence rate than the naive approach. The typical approach to debiasing is to first characterize how that risk representer looks like for whatever functional you care about. And so if you care about some cosmological constant, you would need to characterize what's the risk representer of that functional as a function of the non-parametric components of the data generating process I'm trying to model. And such characterizations have been derived for many functionals of interest in the context of causal inference. But automatic debiasing tries to sidestep this part and says, can we actually estimate that risk representer without even the need to do that characterization? And the idea is that you can formulate the risk representer of any functional as the minimizer of a loss function and hence reduce it to a standard risk minimization or another generic machine learning problem. In particular, you can show that the risk representer of any linear functional is the minimizer of a loss function that takes the square of a candidate risk representers and minus 2 times the functional evaluated at that candidate risk representer. And the reason why this works is because you should think of this loss function as an incomplete square loss. By the risk representer property, for any candidate alpha, the functional evaluated at alpha is the inner product of the true risk representer and that alpha. And so I can replace this second part over there by this inner product, at which point I get exactly an incomplete square loss, which I can complete with A0 squared, and get that any differences in my loss function is basically equal to the mean squared error with respect to that unknown risk representer that I care about. So minimizing this loss is essentially equivalent to minimizing the mean squared error with respect to the target risk representer you care about, and no need to do any math to characterize how that risk representer looks like. Okay, so this, we developed several algorithms for particular function classes for this, using this automatic debiasing approach that perform well and produce state-of-the-art results for causal inference problems. And in the last few minutes, I want to also tell you that, okay, this was just one example of how to do, of when we can do automatic debiasing, but give you the limits of what we know for what types of problems we know how to do automatic debiasing for, which is way beyond that linear functional scenario that I described. So this is what I've told you about so far, that you can do, you can do automatic debiasing for any linear functional of a regression function. You can extend this to say linear functionals when you have covariate shifts, when you care about linear functional over a different distribution than the distribution in which your regression was trained. You can extend this to non-linear functionals. It's just that now you first need to linearize your functional by taking a numerical derivative around some initial estimate of your regression, and then find the risk representer of the numerical derivative. So the same ideas hold for non-linear functionals. You can extend this to the cases where this nuisance parameter is not a regression function, but generically the minimizer of some loss function. And you can even generalize this to the case where this nuisance function over here is the solution to a linear inverse problem. And even when it is, these nuisance functions are defined in recursive ways in some sort of nested manner, where one nuisance function depends on the previous one and so on and so forth. So we have automatic debiasing procedures for all of this class of semi-parametric inference problems. And so with that, I want to conclude that for a large variety of semi-parametric estimates, we can automatically debias them and remove the regularization bias of that is introduced by machine learning estimators. The estimation of the debiasing term itself can be performed with generic machine learning using this automatic risk estimation approach. And the resulting methods give performance that's superior to prior plugin approach in debiased inference. Thank you very much.